Alright folks, hello and welcome to this video example on section 5.1, the laws of exponents. This is an Algebra 1 topic that you've seen before, so we're going to dive right in, and I might move a little bit quickly. If you need to pause the video or rewatch or ask questions in class, that is totally fine. So let's start by looking at what an exponent is. Just recall that when you have an expression like this, x to the n equals y, the x is known as the base, and the n is known as the exponent. The small number that is written above the number, and the entire thing, x to the n, considered as a whole, is known as a power. If you want to be real particular, you could say it is a power of n. Right? So if we say that is equal to a number y, well then y, which stands for the whole thing, is a power of n. Okay, so quite simply, if you have 2 to the third equals 8, well we can say 8 is a power of 3. We sometimes also say 2 to the third power equals 8, or 2 raised to an exponent of 3 equals 8. Just some basics. Alright, so let's look at some properties when we do operations on exponents with the same base. That's going to be the key to most of these laws. So in this first one, we have a to the m times a to the n. What does that equal? And a lot of students end up memorizing these laws and confusing them, at least in Algebra 1 the first time they see them. So what I'm going to recommend to you is, if you ever forget, look back at some examples. We're going to quote-unquote derive them just by looking at 2 or 3 examples for each case. But if you forget, just rewrite these examples for yourself. So if we want to figure this out, let's just say, oh, well, how about x squared times x cubed? What does that give us? And just rewrite it out based on the definition of an exponent. So the definition of an exponent means you rewrite the base the amount of times given by that number, the exponent, in that case n, in this case 2 and 3. So this would mean I rewrite x times x, and I rewrite x cubed as x times x times x. Then use the definition of the exponent to see what the new power is, and this will be equal to x to the fifth. You could repeat this process with different numbers, and you'll notice that the pattern will emerge that you add the exponents. 2 plus 3 gives you 5, and for a product of powers, you add the exponents, and it is a to the m plus n. Alright, and you can look at more examples as needed. Power of a power, we're looking at something like this, x squared to the third power. Or we'll look at another one. How about x to the third to the fourth power? Now, the process is going to be write it out based on the definition of an exponent. So, based on the definition of exponent of 3, we can rewrite this expression as x squared times x squared times x squared, 3 times. And then using our first property up here, product of powers, we simply add those exponents and we get x to the sixth. Similarly here, this will become x cubed, x cubed, x cubed, x cubed, multiplying 4 times, okay, based on the exponent of 4. And then using our first property, this will simply equal x to the 12th. So looking at those two examples, you might see the pattern emerge, and you can look at more if needed, but 2 times 3 gave us our new exponent of 6, and 3 times 4 gave us our new exponent of 12. So, therefore, our answer will be a to the m times n. Or in other words, you take the product of the exponents. That's the law. Law, property, those are all different words. You'll see people refer to these things. They're just facts that we've shown. All right, power of a power. Let's look at one example. xy to the, fourth power. Something like that, raised to an exponent of 4. And now we have 2 different variables, 2 different bases, but they're both raised to the same power, or the power of a power. I'm sorry, there's a typo here. This should read the power of a product. We're multiplying 2 things in parentheses, and we're taking their power, raising them to the 4th power in my example. So again, let's rewrite based on the definition. This is xy times xy times xy times xy. You can rewrite these terms where the x's are next to each other, commutative property, and the y's are next to each other. You'll notice you'll have 4 y's and 4 x's. In other words, it will become, I'm going to write it over here, x to the 4th times y to the 4th, Or in other words, you take each item and raise it to the exponent on the outside of parentheses. And those are the three basic laws of exponents. Next up are negative exponents. Definition of a negative exponent is that a raised to the negative n equals 1 over a to the n. Just like that. That is simply its definition. Students will often confuse this because they'll think that the negative exponent has something to do with multiplying by a negative number, and it does not. Okay, it has nothing to do with multiplying by a negative number. I mean, theoretically, if the base is negative, you might have to do that along the way. But the negative exponent doesn't indicate that. It does not mean multiply by a negative number. What it does mean move the location of the exponent. Okay, that's exactly what a negative exponent means. It means move its location, and then you're going to make the exponent positive. By location, we're either going to refer to numerator or denominator. So in this case, 3 to the negative 2, well, you could consider this whole number over 1. So therefore, 3 to the negative 2 is in the numerator. Well, the meaning of a negative exponent means move it to the denominator and make the exponent positive. Therefore, this would equal 1/9. Similarly, if we had 1 over 3 to the negative 1, the negative exponent is in the denominator. Well, what's the meaning of the negative exponent? It means move the location. So we'll bring the 3 to the numerator and make the exponent positive. So that'll be 3 to the 1, which is simply 3. Okay? You're going to see this in a couple of examples later on. I'm always going to take care of that movement first, as I think it's just good to get it out of the way. Also, for simplifying purposes, no negative exponents in your final answer. Okay? No negative exponents. No negative exponents allowed in the final answer. So just keep that in mind when you're simplifying. Next up there is the definition of a zero exponent. And you'll notice that a to the 0 equals 1, provided that a does not equal 0, that the base is not 0. So no matter what power you have, if you have 234 to the 0, I'm sorry, not what power, no matter what base you have, if it's raised to the 0 power, it will equal 1. Okay, if you have negative 5.17 to the 0 power, that will equal 1. And what students always wonder is, well, why? Like, why is this the case? Why is it defined this way? And the answer to that just has to do with mathematics and mathematicians desiring to follow patterns. And one simple example I can show is with powers of 2. So if we say 2 to the 4th, 2 to the 3rd, 2 to the 2nd, 2 to the 1st, and then 2 to the 0. Let's think about what those things equal. 2 to the 4th is 16. 2 to the 3rd is 8. 2 to the 2nd is 4. 2 to the 1st is 2. And if you follow the pattern, as mathematicians love to do, you will notice that this will give us the next result if we divide by 2. This will give us the next result if we divide by 2. This will give us the next result if we divide by 2. Well, sticking in line with that pattern, we get the next result if we divide by 2. And if you take 2 divided by 2, the result is simply 1. And this pattern can be repeated no matter what the base is, and it will show up. So that's why a zero exponent is defined as 1. It's so that we can still follow our pattern. By the way, if you keep that pattern going, you'll get 2 to the negative 1, right? Because if you take 1 divided by 2, you get a half. Well, that's 2 to the negative 1. 2 to the negative 2, divide again. You'll get a fourth. So the pattern keeps going for all of those different positive exponents. All of those different exponents, negative or positive. Okay, last piece of advice. Please copy the entire chart on page 330. There's a couple of laws I didn't discuss with quotients, and you want to have those all in one place. So copy those into your notes so you have them for future reference. Lastly, we're going to simplify 2 examples. My advice would be pause the video. You try these on your own. Pause the video and you try these 2, and then you can go watch it and see if you got the same answer that I did. Okay, so I'll give you a chance to pause right now. But now I'm going to start solving it myself. And you're allowed to do these in different ways as long as you follow the laws of exponents. Some people like to think about them differently. And my particular desire is to first get rid of all the negative exponents. Sometimes I do this in my head, but for you I will write it out. And that will simply give me a b squared in the numerator and a b to the 4th in the denominator. And the a to the 1 or a to the negative 1 will jump up to the numerator. So what I did there is I moved its location, made the exponent positive, did this same thing, moved its location, did this same thing, moved its location. So I moved all the locations, made the exponents positive. All right, now I'm just going to simplify b squared over b to the fourth. Well, that's two b's that are going to cancel out. Remember, b squared is just like b times b. And then b to the fourth, if we cancel out two of those b's, we're going to be left with b squared. Similarly, here we have 3 a's and 1 a that we can cancel with the 5 a's. That's a total of 4 a's being canceled, which is going to leave 1 a left over in the denominator. If you're using quotient rules, you might be doing some subtraction here, and that should give you the desired result as well. So this will become 2 over ab squared. And that's our answer. Again, there are a variety of ways to think about that simplifying and do the steps in different orders, and that's perfectly fine, as long as you get the right answer. So make sure you simplify it correctly. Lastly, example 2. For this one, order of operations, I'm going to take care of that exponent first and raise, be careful, everything in this numerator and everything in this denominator to that power. And then let's rewrite everything. Also, at the same time, I'm going to get rid of that negative exponent. So that's going to give me x squared over 3y to the fifth. When I brought the y to the negative third, when I brought it down there, it became y to the third, and then multiplied by y squared gave me y to the fifth, times y to the negative sixth over x to the negative 12. Again, I'm going to get rid of these negative exponents. That gives me x squared times x 12th over 3y to the fifth times y to the sixth. Simplifying gives us x to the 14th over 3y to the 11th power. Okay, you probably saw similar problems like this in Algebra 1. I just want to give you a couple examples that you can try and make sure you know how to do. So that is our examples, and now let's summarize the entire lesson. In this lesson, we looked at basic exponent laws, and we did some quote-unquote derivations by looking at examples and seeing what pattern emerged. We then defined the meaning of a negative exponent, and we explained that it does nothing to do with multiplying by a negative number. It just has to do with moving the location of the exponent. Thirdly, we looked at a zero exponent, and we derived that. We explained where that came from the pattern, and negative exponents also come from following that same pattern. Mathematicians like patterns and following patterns to keep things coherent. And then finally, we looked at two examples on simplifying with exponent laws. If you understood everything in here and it came easy to you, that's great. If not, you might want to rewatch a couple of parts. You might want to try some odd problems in the book so you are safe and sound and ready to perform exponent law problems on Monday. Thank you for watching this video lesson.